Hello, students. Today we want to talk about inequalities. Throughout the course, we will use inequalities and we will actually look at more specific techniques as the problems that we solve become more complicated. But if you think about some of the strategies that we use to solve equalities, we'll find that many of those are applicable to solving inequalities. But there are some, I would say, important changes that we have to make note of. And once we have those, then we can actually work on inequalities with confidence and complete problems knowing that we have used good mathematics. So first, what I want to do is share with you some of the major differences. Now, I'm sure in your previous classes, you have probably used these results. And I want to talk a little bit about them so that we have a little bit better foundation. So let me share my screen. Now, what we have here is a theorem, or actually two. The first theorem is that most of us learn when we take Algebra 1. Maybe we don't think of exactly why it's true, but intuitively we accept it. The key here is that if we start with A and B as real expressions, that is, they could be numbers or expressions, such that A is greater than B. So we have that premise, A is greater than B. And then suppose we take some expression or number, C, that's negative. So remember, when we say something is negative, we say that it is less than 0, okay? Again, all real expressions, A, B, and C. But then, of course, if we multiply the inequality by an expression or number that is less than 0, we remember that that particular operation will reverse the order of the inequality. So if we have A is greater than B, then CA should be less than CB. Again, when you think about a real number being larger than another one, that makes sense. But when you apply negatives, the larger real number becomes a more negative real number. So it will be less than a real number, for instance, that's less than that initially. So let me just write down a very simple example here. Say we have 2 is less than 5. Very simple example, and just using numbers. And then if we multiply by a -1, so 2 times a -1 should be greater than 5 times a -1, or -2 greater than -5. So this you have no trouble believing, but it's true in general. That is, when you apply a negative to a number that's positive, which is actually smaller than some other positive number, the negatives flip the order. So now we see that -2 is larger than -5. So the idea that we do this is not because we think of it as maybe just good sense. It actually relies on the axioms of the real numbers and is therefore a theorem. So lots of times when we work with mathematics, our intuition really does pave the way, but we often have to remind ourselves that these particular results must be applied. So, for instance, your teachers in the past may have said, well, multiplying by a positive expression preserves the inequality. That is, nothing reverses, but an expression that is less than 0 or negative reverses the inequality. And what I wanted to do is say a little bit about this particular result and why it's true, and then work several examples so we can build some confidence with the inequalities. Like I say, later on, we will add more complexity to the inequalities. We won't be changing anything, but we will add some more ideas that will help to make our process efficient. Now, one thing we have here, what I want to state is the script P. That's what we call the positive real numbers. So just the script P would just be 0, not included, out to infinity. Okay, so when we use inequalities, we necessarily use interval notation. We will use the parentheses when we do not want to include the endpoint, and then we'll use brackets when we want to. Now, the thing is, infinity is not a number, so it never has anything except a parenthesis. You can't bracket infinity because it's not a number. It simply is the behavior that you can place any number here that's bigger than 0 and go ad infinitum. So, of course, the positive real numbers are not bounded. We know this. The real number line is not bounded. So, in order to show that, we use the so-called infinity symbol. And I know you've used this before, but we will certainly continue to use this in the college algebra class. Now, there are two axioms, ladies and gentlemen, that are considered to be truths for the positive real numbers. That is, and I'm using Greek letters here. We always need to learn some Greek letters because when we get to trigonometry in pre-cal, we'll have plenty of opportunities to use Greek letters because they've actually become standard in trigonometry and even in calculus. So if we have two positive numbers, alpha and beta, it will be a truth that the sum of alpha and beta is also a positive number. That is, if you add any two numbers that are positive, the result is positive. We consider that to be a truth. We do not prove that. The second truth is that if alpha and beta are positive real numbers, we consider the product, that is the product alpha times beta, to also be a real number. So what we often say, and this is a phrase that we'll get used to, we'll say P is closed under addition. So if you take any two elements and add them, you still have an element of P. So that's why we say it's closed. That operation will not take you beyond the positive real numbers. You stay within the positive real numbers. And then we say P is closed under the second operation here, which is multiplication. So many times properties of sets have to do with closure under certain operations. And so that's why we think of these axioms as basically closure axioms. Now, to prove the result about multiplying the inequality by the expression less than 0 reverses it really just requires us to use the axiom 2 from the set of positive real numbers. So let's just look at this, and I think you'll be astonished as to how simple this is, but it is a little bit subtle, and we, like I say, we need to start somewhere so we can start building levels of abstraction. What we find, ladies and gentlemen, is that abstraction is the perfect place to work with ideas, with mathematical ideas, and then we bring them back into the real level of a problem and find that we now have excellent techniques to work a problem. We don't have to start at square one. We use the theorem and it makes the problem solving more efficient. So what we can see is that if A is greater than B, then of course, subtracting B from both sides, A minus B will be positive. And so we can say that A minus B is an element of the positive real numbers. Likewise, if we start out with C being less than 0, then its additive inverse by definition, must be positive. For instance, if we think of a negative number like -5/2, okay, if we take its additive inverse, that undoes the negative, and we have 5/2. So the additive inverse of a number that's less than 0 will always be a positive number. Okay, so this is really the key here. And then if we go to axiom 2, that would mean that the product of A minus B and the additive inverse of C would again be greater than 0. That is, be a positive real number. So this inequality right here holds the key to this result. Okay, so now all we do is apply the distributive law. We do A times the additive inverse of C, which is the additive inverse of AC, or you can do a negative if you like. And then, of course, the negative B times the negative C, the negatives absorb. That's another theorem about real numbers, and we just get positive BC. So now what we see in this particular case is that, how does this relate to this? Well, then let's just go ahead and add AC to both sides. Then we have BC is greater than AC. And of course, I've written these in different orders, but this is exactly the same as this. You know, you can flip it around and write it with the C before the A, less than CB. So they look the same. Again, remember, with inequalities, you can write them in any order you like, as long as you preserve the direction of the inequality. That's really important. So what you're seeing here is that this result is actually very straightforward to prove, as long as you make the assumptions about positive real numbers and basic ideas about real numbers. Okay, so there are many properties of real numbers that are quite unique and make solution of equalities and inequalities very efficient. However, we have to make sure that we abide by those properties, because if we fail to do that, then our work is not correct. And so we want to make sure that we apply the properties well. Now, one other result here, which is very easy to prove, I just want to state, it's called, in some cases, the reciprocal theorem. Now, this again is a very valuable result in the pre-calculus sequence, including college algebra, and also in the calculus sequence, because many times we find it convenient to reciprocate an inequality, that is, reciprocate the actual expressions on either side of the inequality. That can be very, very useful. So how do we know that we can do that? When is this something that's available to us? Well, what we can do, we've got two cases, and this may be a little bit redundant, but it's better to state them. So we're going to assume that if A and B are positive as numbers or real expressions, then we can apply the reciprocal rule. The only problem with the reciprocal rule is that if the expressions have different signs, that's when it does not work. So we must be careful that the expressions have the same sign, and then we can reciprocate. So now, if we start with A is greater than B, then 1 over A will be less than 1 over B. So not only do we have the reversal of the inequality, we have the reciprocal of the expressions. So again, this is a result you have used before, and we want to have it available. Just because we have results available does not mean that you're going to use them with every problem. But we need to be aware of them because they can be very, very useful. Now, another thing that we want to show is that it certainly could be the case that both of the expressions are negative. I mean, for instance, we could just state the theorem that both expressions have the same sign and be done with it. But I've just stated the positive case and then the negative case. So if this is true, then A greater than B would be equivalent to the reciprocal of A less than the reciprocal of B. So notice when we reciprocate, it's like multiplying by the negative here. The direction of the inequality reverses. Okay, so that should tie in the procedure that we have, like I say, in the first result here with this result. So they're very similar. Okay, but we have to again just remember the restrictions here. So when you start to apply this, you have to make sure that it actually makes sense. Both expressions are positive or both are negative. That is, they have the same sign. So let's practice with some of these examples using some of the results, or actually problems, from the lecture notes. So let's start with the first one here. Now, like I say, some of them are very straightforward, but we want to make sure that all of our techniques are good. So we'll start with simple and improve the difficulty as we move through. Now, just remember, as we continue to work through the course, like I said before, we will add more complexity. It will not mean that we relieve ourselves of any of the results that we already have. We may just have to add some new strategies or think about how we can envision computing a sign. Now, when you look at this particular inequality, we're going to solve all of these problems in the real numbers. The imaginary numbers, or the complex numbers, are not ordered. We don't have the ordering properties. So we have to stick to the real numbers here. So what we can do in this case is just go ahead and collect everything, multiply and collect terms. So equivalently, and let me just write up here, solve in the real numbers. So we have 8 minus 7, and then minus minus, plus 7x less than or equal to 7. Now, when you look at this, the first thing we can do is collect these terms. They're the same. So that'll give us a 1 plus a 7x less than or equal to 7. Now, what I want to show you is a technique similar to the zero product. It's basically zero product, but we've got this inequality, so our answers are going to look a little bit different, because what we're going to think of is when we create a zero on one side of the equation, that's going to mean that we have what we call a boundary value. Now, of course, when the equations are this simple, these inequalities are so simple, we usually don't do that. And I understand why you think I just need to isolate x and solve it that way. But let me show you a technique that we've already been using. So now, of course, if we subtract the 7 from both sides, we'll have a 7x minus a 6 less than or equal to 0. Now, of course, we can factor this. Let's factor the 7 so we can compare this to the zero product of the inequality, of the equalities. So if we were solving an equation and we had equals here, you would say, okay, by zero product, x equals 6/7. Now what we're thinking of is the 6/7 is a boundary value. And that's what I want to make you aware of now, because this will be a technique we'll use later. So what we can say is boundary value. So the solution intervals will have boundaries, so to speak. So we're thinking of the 6/7 as being a boundary of one of those intervals. Now, a lot of times I will just say BV like that for short. Okay, so you don't have to write as much. So now we've got 6/7. So you could say BV is 6/7. And then we can think of a number line. And of course, this is more complicated. You're thinking you just divide and you're done. Well, notice now, if we were to look at the sign of this, the 7's positive. But of course, if we were to put a number much larger than 6/7, like 300, we would be positive. So we could say just put a line or a curve here, meaning positive. And then, of course, this particular 0 here has odd multiplicity, so that the sign would necessarily have to change at 6/7. That's a very useful property. Multiplicities of zeros help us to decide whether or not the curve will cross the x-axis or just touch it. Even multiplicity would mean a touch. The odd would mean a cross. But that does require that you at least figure out one on your own. And we just usually take an easy one, like, taking a large number over here and noting that we have positive here and we have negative here. So again, even though this is a very simple example, I want to push this idea, because there might be cases, and there will be, when we have several BVs. And then you can't really just solve. You've got too much complexity. So we have to do a boundary value sign test. So now we can see that here negative means less than 0. So we know that this inequality is true when x is 6/7, because that's equal to 0. And we know it's true when x is less than 6/7. So now we'll say x element of negative infinity to 6/7 with a bracket. The bracket meaning we include the 6/7. Now, another thing you may notice here is that when I say x element of, that's a little additional information to say that all x's that lie in this infinite interval solve this inequality. So what's important is to use the parentheses and the brackets to notate the actual solution interval. Now, of course, just like equations, inequalities don't always have solutions. So don't worry if you get the empty set. It's not a bad thing. I mean, it happens. So let's look at another one. Again, feel free to just divide here. It's okay, but I want you to be aware of the boundary value technique. Now, in some cases, when we have a compound inequality, we'll just deal with it as we have in the past for efficiency. So let's look at another one. Again, very simple, but very good techniques. X/4 greater than or equal to 3 minus x/16. Now, when we look at this, there's what comes to mind is what we do when we talk about solving equations. Usually what we like to do is clear denominators. And so there's nothing any different when we look at inequalities. That is, when we think of it that way, we can go ahead and clear the denominators, maybe to simplify. Again, that's completely up to you, but we find it to be very useful. So now we'll just go ahead and multiply both sides by 16. So 16 times x/4. I'll just go ahead and write this out. And then, of course, we have 16 times 3 and minus 16 times x/16, putting the dots just to emphasize multiplication. So now, of course, the 4 absorbs into the 16 to give us a 4x. And then, of course, 3 times 16 will give us a 48. And then, of course, over here, the 16s absorb, okay, just like that. And we have minus x. Now, what's interesting about this particular problem is that it's starting to look just like this. So let me just advise you, if we go ahead and look at it like this again, we can get used to the BV technique. So now first we're going to add x to both sides, and then, of course, subtract the 48. So equivalently, we get x plus 4x, which is 5x, minus 48. And this will be greater than or equal to 0. So again, I'm trying to get you used to BVs. So now if we factor the 5 times x minus 48 over 5 will be greater than or equal to 0. So now we have a boundary value of 48 over 5. So this is just like zero product. but we're going to have real numbers for which the expression is undefined. So you might be thinking, why do we care about these? Why do we call them boundary values? Because these are potential real numbers for which the expression can change sign. Like I said before, that will not always happen, but we need to check that. We need to check for the change in sign, because that will determine how we create our solution interval, if indeed it exists. So now we've got the boundary value, so we can just do the same thing we did before. We have 48 over 5. So of course, if you put in like 100 here, you've got plus, and then of course that's a multiplicity 1. So you've got plus and you've got minus. So now, of course, this will be greater than or equal to 0 when x equals 48 over 5 or bigger. So this would imply, or if and only if, x is an element of. Now, of course, we can include the 48 over 5 because of the equals to. 48 over 5 infinity. So again, feel free to divide like you normally do with equalities, but just know that this BV technique will be extremely important as the inequalities become more complicated. They won't and when I say complicated, that may not be necessarily true. There'll just be more of them, okay? More BVs. So we have to adopt a method that will allow us to determine sign efficiently. So it's good to go ahead and start thinking about what they are, even in these simple cases. Now let's look at another one. Let's see here. We've got a compound inequality. So I'll need a little bit more room here. Now, like I said before, in certain cases, we need to kind of maximize efficiency. And so with compound inequalities, we may just say, okay, if it's easy enough to work on all 3 sides at one time, we'll do it. Let's see what we have here. These occur a lot in the calculus. So we have negative 15 less than or equal to 9 minus 4x less than or equal to 25. Now, again, when it comes to solving equations or inequalities like this, what we want to do is remind ourselves that how we choose to solve it is our own signature. So you might look at this and say, well, it doesn't look like we have any common factors, like we can't divide through. But if you like, you could go ahead and flip all these around to get a positive value for the coefficient of x. So let's start by doing that. So we want to multiply by -1 in a symbolic gesture, now that we know what happens. So -1 times -15 will give us a positive 15. And then, of course, by multiplication by the -1, this will reverse. And then, of course, hitting this with the -1 flips the 4x and the 9 to give us that symbolically. And then, of course, here we'll have greater than or equal to -25. So this results by multiplication by -1. So what's important here, if you go ahead and write in the multiplication as an additional step, you must necessarily flip or reverse the inequalities, because if you don't, it's not correct. So what I usually tell students is, when we're just hitting things with a -1, which is a common process, we can just think of taking the opposite sign of each of the expressions and then flipping the inequalities or reversing them, and we've got a more clean equation. Now, of course, this is very straightforward, and you're thinking we've got 2 for the price of 1. We have this inequality right here, and we have this one. But due to the simplicity, we can solve them simultaneously. Now, of course, if the expressions get more complicated, we may have to look at this one separately, and then look at this one separately, and then intersect the solutions if they exist. So now we can go ahead and add 9 to both sides, because we want to isolate the x in between. That would be the most efficient thing. So 15 plus 9 is greater than or equal to 4x is greater than or equal to negative 25 plus a 9. So very straightforward. Now, of course, the 15 plus the 9 gives us a 24, greater than or equal to 4x. And then, of course, now here, this just gives us a negative 16 if we add 9 to negative 25. Now, at this point, this is where we like the efficiency of the so-called old method, because we can get to an answer very quickly. So now, in order to isolate x, we can simply divide each side or multiply each side by 1/4. So equivalently, we have 24 over 4 is greater than or equal to 4x. I'll go ahead and write this in over 4 is greater than or equal to negative 16 over 4. And we like that. So let's just go ahead and do this one first. We'll have negative 4 less than or equal to x less than or equal to, of course, 4 into 24 is 6. So I just flipped the inequality around. I mean, there's nothing wrong with this, but you're kind of accustomed to this. So feel free to turn things around if you like. But we see by the efficiency of simply noting that we have two inequalities built into a compound, the nature of the inequality is simple. And so we can use a very straightforward technique and be done with it. Now, of course, if the separate inequalities are more complicated, then we have to look at each of them separately and then combine them, because the only way we'd be able to combine these is through an intersection. That is, where do the solutions for each inequality overlap? But here, with this method and the simplicity, we get a solution very quickly and very neatly. And so now, of course, this would just mean x lies in this interval, negative 4 to 6, again with the brackets. Now, one thing that's interesting about this particular problem is if you solve it by separating into two inequalities, you'll get the same answer. But here's what I want to say that's very important about this. Let me organize my papers here. I'll make sure I've got all the ones that I want to share with you, because I've got a new one that I want to do towards the end, but I want to make sure that I have all of this. So yeah, that will work. Yeah. Okay, is that what I want there? Yeah, there we go. Cool. Now, like I said before, if you just want to practice doing separate inequalities and then intersecting them, you'll still get the same answer. And that, you might think, well, that's a little bit much, Professor Hollis. But I don't want you to shy away from it, because there will be cases where we'll have to do that, and we'll work on some of those. So let's look at another one. So we've got negative 4 less than 4x minus 8, another compound, divided by 5, less than 0. Now, again, we want to solve in R. If I'm not stating this explicitly, solve in R. Now, when we look at this, we're thinking, okay, this looks like the last one, a little bit different, maybe a little bit simpler. But first, we can notice that, again, we've got some extra stuff here. For instance, we've got a 4 and a 4 here and a 4 here. So we could reduce some of these numbers. You don't have to, but let's just go ahead and do that just for practice. So we have, if you like, a 4 times a negative 1. And then we have the 4 times the x minus 2. Just factor this. And of course, we'll take care of the 5 downstairs. We'll just do this, you know, in small steps, as sometimes they say, baby steps. Don't worry about just knocking a home run right away. Now what we can do is, if we now divide by 4, of course, you know, the dividing that by 4 is still 0, but these 4s just absorb. Now, if you want to get rid of these additional factors, you can. And you know what I'll do, since I did it for the other one, let me just go ahead and fill this in so we can just always rewrite 0 as 4 times 0, right? So we'll do that, and we'll absorb that also. So now what are we left with? We're left with a -1 less than x minus 2 over 5 less than 0. Now we're like, okay, you know, we'll address the 5 now. So if you like, just go ahead and multiply through by 5 so we can dispense with the fractions, just to make it as simple as possible. So now multiplying -1 by 5 gives us a -5. And then, of course, it absorbs here x minus 2. And then, of course, the 5 times the 0 is just 0. Now when we look at this, it's like, where's a similar thing? Like right up here, but even simpler. Now we'll just add 2 to all sides here. So we get -5 plus 2. Of course, you can do some of these in your head, but, you know, go ahead and write these down, 0 plus 2. And now, of course, we have a -3 less than x less than 2. So that would mean x would lie between -3 and 2, exclusive. That is, we don't have equal to here. We have strict inequalities. So the solution set would be an open interval. One nice thing about the topology of the real line is that when you've got your standard open sets that don't include endpoints, those are the open sets, and of course there are other types of open sets. I mean, we will discuss that tangentially, but the idea is that using the brackets and the parentheses allow us to state the type of solution set. Do we include the endpoints? Do we not include the endpoints? Is the subset, or is the solution set infinite? Do we have an infinity in it? Again, remember, infinity never uses a bracket because it's not a real number. Now let's try another one. The reason I like doing the compound inequalities is that they do occur in mathematics, especially in calculus. And so we want to be familiar with them. They're not overly difficult as long as they're not too complicated. And then, of course, you could look at these and say, well, you could create one easily that would have no solution. But again, I want you to feel free to break them down into 2 inequalities. For now, you're probably thinking, well, these are straightforward enough. I'll just continue with this technique. Now, just like we did before, we've got 2 options here. I mean, we've got a very simple coefficient of -1/2 here. So what we could do is just go ahead and multiply through by -2. And that way we could just clear out everything. Now, of course, when we did -1, we did that symbolically. But let's go ahead and write this out. So our goal here would say, if we just have a coefficient of x that's 1, that's really, really simple. So let's do that. So we're going to have -2 times -2. Then we have to reverse, and then -2 times 1 minus 1/2 x, reverse, and -2 times a 5. Now, this is writing it out. Before, when we multiplied by the -1, we just did that symbolically because that's easy to do. But here we've got a -2. So let's write it out. So remember, we've multiplied the inequality by an expression that's less than 0. So these must reverse. So now negative gives us a 4. And then, of course, when we multiply here, the -2 and the -1/2 absorb to give us an x. And then, of course, -2 times 1 is just -2. And then lastly, -2 times 5 is a -10. Well, that was worth the trouble because now all we have to do is add 2. So 4 plus 2 is greater than x is greater than, in this case, -2 plus 2. And so now we've got 6 greater than x greater than -8. Now, if you want, you can go ahead and flip it around. So -8 less than x less than 6, which is equivalent to an interval, of course, open interval, x element of -8 to 6. Now, again, I want to emphasize, just like solving equations, you have many chances and many different avenues to affect a solution. Just note here, since the degree of x or the power of x is 1, these are very simple inequalities. So we can deal with the two inequalities simultaneously. They're that straightforward. So just remember, not all inequalities will come in these nice packages, okay? But we want to at least start to develop our techniques with inequalities that have particular properties so that you can become more confident in using the properties that are unique to inequalities, okay? So again, the main thing here is the techniques of reciprocation and multiplying by a negative number. We clearly won't use the reciprocation as much. And then sometimes you may be using a form of it, but you may attack the inequality a little bit differently. And so it doesn't specifically use it, but that's okay. When you need it, it will be available. Okay, let's look at another one. These are some interesting examples from the notes I think are good. So here we've got interesting problem, kind of looks like the last one, but a little bit different. 8x plus 4 is less than 0. So when you look at this is a different kind of inequality compared to the last one. So we're just going to say solve in R. So what's nice about this particular type of example is that when we think about finding values of x that will work, we first have to notice that 1 is a positive number, right? 1's positive. 1 is greater than 0, but the expression 1 divided by 8x plus 4 is negative. So that means that 8x plus 4 has to be less than 0. But before we do that, let's just go ahead and do what we did before and get rid of some of the baggage. So we can factor the 4, and this will give us a, well, let's do this. Let's be even more bold here. Let's just go ahead and factor the 8. And that'll give us a 1 plus a 4 over 8. Won't skip any steps here. And then, of course, well, I guess I should write my x. It's like the coefficients absorb, but the x didn't go anywhere. Okay, so now, baby steps, 8x plus 1/2, just to show that we can rewrite things and make them more user-friendly. Now, of course, we can get rid of the 8, just multiply both sides by 8. So this will give us 1 over x plus 1/2 is less than 0. So I want you to feel comfortable with working with inequalities. That is, if you factor this, and then, of course, multiply through by 8, the 8's gone, you're got all the clutter done. And now, again, we go back to this and say, well, 1 is positive, but if this expression must be less than 0, x plus 1/2 must be negative. So equivalently, x plus 1/2 must be less than 0. Now, of course, we can do BVs here, but we've done all this extra work. Let's just go ahead and transpose to the other side, or think about the BV would be what, -1/2 in this case, because that's what would give us a 0 there. But just to change it up a little bit, let's just go ahead and subtract 1/2 from both sides. So here's a direct computation. So any x less than -1/2 would satisfy this. Now, of course, if you want to just go ahead and write BV, the BV would be -1/2. And of course, if we did the plotting, -1/2, and then of course, if you put in, 500 here, that would be plus, and then of course, you've got 1 degree here, multiplicity 1. So you've got plus here and you've got minus here. And so you get the same answer. Now, of course, any x less than -1/2, of course, this is negative. So the negative corresponds to less than 0. So either way you want to do it, you've got the answer. So now x is in the infinite interval, -infinity to -1/2. So this is really important, ladies and gentlemen. This is what I'm talking about. If we have extra BVs hanging out, then we've got to say, okay, where are the possibilities that things would go awry? So notice here the way this is written. We see that this particular expression is undefined at -1/2. I mean, we can't divide by 0. So this is an instance where BVs can take on two qualities: a 0 of the entire expression, or a 0 for which the expression is undefined. Now, of course, the way this is so simple, we just say, well, okay, if this particular expression is going to be less than 0, the x plus 1/2 has to be less than 0, because the 1 is positive. So now we're kind of looking at it like just pulling the x plus 1/2 away. But I want you to look at this and think about what the arithmetic is saying. You could just go ahead and transpose and get your answer this way, or you can think of the BV. Either way, I want you to start thinking about the boundary values and how we can do a simple sign test with a number line and make the process very efficient. Okay. So now let's look at another one that has the same topic, but it's compound. So we've got 0. These are all excellent examples from your lecture notes. You have a really, really excellent book that gives you plenty of good examples and states things in a very clear and concise way. That one good thing about STEM mathematics is having a good source. Having a source that you can read for examples, having a source that you can read for definitions, things of that nature ground you. And then, of course, when you're done with the class, you can get an electronic copy of the book, or you can find an edition, a used edition, and have that in your library. So it's always good to have a math book. They don't really go out of fashion. And they're always great when you need review as you move up in your courses, especially when things get rusty. Now, when we look at this, we have to think about this and say, if we apply the techniques up here, then we're in good shape. So notice, both of these here must be positive. That is, 5/x is greater than 0. And 8/9, well, that's clearly positive. I mean, that kind of overstating the obvious. But what we're seeing here is 5/x is between 0 and 8/9. So positive, positive. So when you want to look at that, you can think of reciprocal. Okay. I mean, that's one way to look at it. There are many ways to check this out. But notice here, I'll just say observe 5/x is positive, and clearly 8/9 is positive. So this extra inequality here is kind of like, here's some information. It is a zero, it's a real number, but it's a special number. Zeros are always useful in inequalities. Why? Because we compare numbers, signs of numbers relative to zero. A number or expression larger than zero or greater than zero is positive. A number or expression less than zero is negative. Okay, that is very important. Those order properties allow us to solve inequalities. So now if you want, we can reciprocate. So apply reciprocate, just write it out, reciprocate. So now this will be what? X over 5, and then you have to flip it, is greater than 9 over 8. Okay, so now you're thinking, well, can I just really cross multiply here? And the answer is yes, because all you need to do now is isolate the X. Now, again, I'm not requiring you to do the BV technique every time. So if you want, you can just go ahead and multiply. So now just get rid of the 5, multiply both sides by 5. So X is greater than 9 over 8 times 5. And that's just 45 over 8. So now X must be greater than 45 over 8 for this inequality to be valid. So this would imply, if you will, X element of 45 divided by 0, comma, infinity. So again, what's really important here is looking at the fact that just like an equation, the inequality and how the symbols are set up and displayed give you much information. But you don't look at the given and say, well, I'll try to guess a solution. What you try to do is simplify it. You want to write down an equivalent inequality well, exactly, that's it. I mean, I can't really say anymore. You want to write down an equivalent inequality that is what? Simpler. And if it's simple, then you can say, oh, X must be bigger than 45 over 8. Well, that's what this is saying, but it's hard to see that looking at that. So we reduce the complexity of the given problem to something very simple. Now, of course, if you wanted to, you could just take everything on one side and factor and still get a BV of 45 over 8 and do the same number line technique. But you don't always have to do that. I want you to be aware of it. So just remember, the BVs will come back as we have expressions that have several places where the expression is 0, maybe a couple of places where the expression is undefined, and then we can plot the numbers and do a really simple sign test using multiplicities of zeros, which we're going to say more about as we continue with the course. So for right now, these are excellent techniques which you can use to get used to the idea of the boundary value. Now, there's one more example that I want to cover that has to do with, in this particular case, a problem that's stated in such a way that you can use some of the theorems. And here it is. It says, suppose, very simple, and I don't want you to be afraid of these kinds of problems. I want you to say, well, I can do this. Suppose that X is between 2 and 5. And we want to determine A and B, real numbers, such that this will be easy to build. I'll show you how. Such that, in this case, A is less than 3 divided by X minus 7 less than B. So when you look at this, what we want to be able to do is to build this inequality, but we want to build it in steps. So just remember that the goal is this, but we don't just write it instantaneously. When you think about doing problems and solving equations, you don't start with the equation, boom, there's the answer. If it's a complicated equation, then you have to go through the steps of simplifying things. Now, when you want to build an inequality, you take the same approach by building it step by step. So if we look here, first thing we want to build is just x minus 7. We can build that easily by subtracting 7 from each side of the inequality. So let's do this. So in this case, what is our first step? I'll just say this implies 2 minus 7 less than x minus 7 less than 5 minus 7. So basically, we subtract 7 from the given. So this is all we have right here. That's what we know about x. We can say it's between 2 and 5. It lives in the interval from 2 to 5 exclusive. And so if we're interested in the quantity x minus 7, we could simply subtract 7 from each side here in the inequality and figure out where that lives or where that it resides. So of course, 2 minus 7 is a negative 5. Very simple. And then of course, x minus 7. And then 5 minus 7 is a negative 2. So just like we've talked about before, we have x minus 7 between two numbers that have the same sign, negative. So use reciprocal rule. Reciprocal rule or reciprocal theorem, whatever you want to call it, or just reciprocate. So now when we flip, when we do the reciprocation, we have to flip things. So it's easier if you just kind of reverse it with everything reciprocated. So negative 1/2, this just makes it look a little more user-friendly, less than 1 over x minus 7 less than negative 1 over 5. And I'm just going ahead and putting the negative upstairs instead of leaving it with the 2 and the 5. So again, when you flip things, these turn around. And so then what I did was just take the mirror image of that. So you can think of just flipping the inequality around through its image in the mirror. And upon doing that, and reciprocating each of these expressions, you've got an equivalent inequality. Okay, so again, the reciprocal theorem is really useful. And now, if you compare this to this, the only thing you have to do at this point is multiply by 3. So I'll just write it out: multiply by 3. And that, of course, is a positive number, so that doesn't change anything. So we'll have a negative 3/2 is less than 3 over x minus 7 is less than negative 3 over 5. So now we see that 3 divided by x minus 7 will reside between the real numbers negative 3/2 and negative 3/5. So this if and only if a equals negative 3/2, b equals negative 3/5. Now, when you work with limits and you're trying to figure out, for instance, a particular value of delta, which has to do with the actual limit definition, you often have to work with the compound inequalities just like this. And we will refine techniques when we apply functions or whatever. If we apply increasing functions to an inequality, then of course the inequality would be preserved. So we will add additional techniques as we learn more about functions and we learn more about equation theory, because what we want to be able to do is to manipulate inequalities that help us solve calculus problems. And of course, in STEM, the use of calculus is very important. So again, think about these examples just like doing equations. All of those properties that we use are still valid. However, we just have to make a few adjustments. If you reciprocate an equality, you just reciprocate it. There's nothing to flip, okay? Works very nicely. If you multiply an equation by a negative number, okay, the equals is still equals, okay? We just have to remember in the cases for inequalities, we reverse the inequality. Those are the exceptions that we must abide by. Otherwise, we write down things that are incorrect. Now, let me just also caution you, don't always assume that an inequality has a solution. I mean, equations have no solutions. So be aware of the fact that even if you make up an inequality, maybe you just you write down things very creatively and you try it and there is no solution. I mean, that will happen. That one thing that's interesting about learning STEM mathematics is that as you move through the process, you'll be able to go back to an earlier course and construct problems with more confidence and more expertise. When you're learning things for the first time, you're probably not that interested in doing that until you build that level of confidence. So I hope you've enjoyed this lecture on inequalities. This will be a good way for us to begin our progress into more complicated inequalities. Just remember, when we take the calculus and we talk about limits, we talk about derivatives and things, sign assessment is very important. And we want to be able to do it with confidence and know that our calculations are correct. So more to come soon. We'll see you later.